Hello, my name is Asma, and I am a PhD candidate in the Department of Mathematics. Today I will talk about data-driven optimization framework towards personalized treatments in HIV. This is a joint work with my advisor, Professor Sophie Croy. Our primary goal is to devise an optimal personalized treatments for HIV patients. In order to do that, we first estimate the patient's specific parameters in the ODE system. Our method is novel in the sense that most existing parameter estimation techniques are traditionally done through clinical trials, and most mathematical models only determine the efficacy of a drug, not its dosage. In order to achieve our goal, we need to solve two inverse problems. We use two mathematical models. The first one is the basic HIV dynamical model, where we have T1 tilde, T2 tilde represent the healthy cell, and I1 tilde, I2 tilde represent the infected cells, and we have V that represent the virus. We also use the combination therapy model, where we have T tilde, I tilde, and V tilde represent the healthy cells, infected cells, and virus, respectively. We also have URT, U tilde RT, and U tilde PI represent the treatment. Before we formulate our optimization problems, we first non-dimensionalize the system. Non-dimensionalization simply means removing the physical dimensions from our systems. After the non-dimensionalization process, we can formulate our optimization problems. We have two nonlinear constraint optimization problems. The first one is for parameter estimations, and the second one is for optimal drug dosages. We solved our problems numerically using projected nonlinear conjugate gradient optimization scheme, which is a generalization from the conjugate gradient method. In order to obtain the solution, we generate a set of synthetic data measurements by solving the original ODE. Starting the algorithm with the initial guess factor theta naught that is given in the first column, we obtain the estimated parameters vector theta u star that is given in the second column, which is very close to the true parameters vector theta u that is given in the third column, with relative L2 square error equals 0.121644. For the data fitting, we found out the data is in blue and the estimated solution in red. They almost overlapping, with the relative L2 square error as given in the table. For optimal treatment, we consider undetectable level of the virus to be less than 0.2 copies per microliter. The initial time considered here was at day 13, and the initial viral load is 9,780 copies per microliter. The treatments considered here are EFV from the reverse transcriptase inhibitors class and ATV from the protease inhibitors class. We found out after giving the treatment EFV and ATV, the healthy cells T increased after 90 days. And also the viral load decreased after 90 days. Our future goal is to determine optimal treatment strategies using a stochastic mathematical framework. The stochastic mathematical framework will be based on the Fokker-Planck partial differential equations that represent the evolution of the associated probability density function. The stochastic framework will provide more accurate results. Thank you for listening.